Hello, everyone, and welcome. Thank you for joining us today, and we hope everybody is safe and well. I'm Paul Darsh. I'm the Director of Marketing here at John Brooks, and John Brooks is a Canadian provider of fluid handling solutions for the industrial and municipal applications that involve pump and pump systems, filtration equipment, spray nozzles, valve actuation, and heat exchangers. Today's webinar is part one of a three-part webinar series that will present a comparative overview of gravity sewers and low pressure sewers. The goal of the series is to leave you with insights and information on how to obtain lower construction and social costs, fewer community and environmental impacts, and the least amount of overall disturbances when considering new or rejuvenated wastewater collection projects for communities. We're pleased to have with us today our main presenter, who is Keith McHale. Keith is with Environment One Corporation, which is otherwise known as E1, and is their application engineering project manager. For those of you that don't know, E1 is a manufacturer and provider of products and services for the disposal of residential sanitary waste. Keith is a professional engineer with 30 years in manufacturing and consulting engineering, all focused on wastewater collection and treatment. And we also have on the panel today Stefan Fedev and Martin Turbide from John Brooks. John Brooks is a representative for E1 in Canada, and those guys are on the call to assist Keith with any questions that may come up. So a little housekeeping before we begin. Your mics will be muted by default for the duration of the presentation. Please use the Q&A icon on the Zoom meeting control bar on your screen to submit any questions you might have. Keith will be presenting for roughly 45 minutes or so, and Keith, Steph, and Martin will be monitoring the Q&A chat box, and they may decide to answer some of the questions immediately as they come up, or they may wait till the end of the presentation. We do want to respect your time commitment and the 1 hour schedule, so if there are any questions that are left unanswered after the 1 hour, we will address them in a follow-up email to the audience. And today's presentation is being recorded, and we will send you a link of the recording to all the attendees today so that you can review it again at your leisure. And finally, part two of this three-part series will be held on Thursday, May 14th at 2 p.m. Eastern, and invitations to register for that session will be going out soon. So again, thank you for attending, and with that, I will turn things over to Keith.
Thank you, Paul. I appreciate the opportunity to be here with you all today. Thank you to John Brooks for hosting this and giving us, E1, the opportunity to talk about pressure sewer systems. As Paul mentioned, this is a three-part webinar series, really going over kind of an overview of wastewater collection, focusing primarily on gravity sewer systems and low pressure sewer systems. And what we're going to do today is just really the larger overview of wastewater collection, why we need it, what are two of the key alternatives, but we'll also mention as we go through there that there are other sewer systems. The next part two, we'll go into a deeper dive of sewer systems, and here we'll get into a little bit more details on the differences between gravity sewer and low pressure sewers, looking at factors such as operation and maintenance, how a system is designed, what are the individual components of the system. And then part three of this will kind of gear us towards the analytical part of it. So we're going to go through on parts one and part two with the concepts of two types of sewer systems. And then part three, we'll get to the part of, making a decision. And what we talk about when we do that, the triple bottom line evaluation, as Paul mentioned in the introduction, low social cost, environmental cost, and then of course the economic cost. Those are the triple bottom line where you look at not just the capital construction costs that as industry we're used to doing for many years, if not decades, but we want to also look at when we have public infrastructure, what are the social and environmental costs as well. And then we'll look at a life cycle cost analysis that provides that economic evaluation to evaluate different sewer systems and how we would get there. So today, as I say, today is just kind of the big, broad overview. When we look at our wastewater management alternatives, and generally we've got two components for wastewater management. That's a centralized system and an on-site system. Now with the centralized system, we're really just going to be focusing on the collection part of it. With a sewer system, it's going to go to a treatment plant. We're not going to touch on that at all. On-site systems, when we talk about wastewater management, include the disposal part as well, because everything is done on site. Within Canada, I've done a little research recently, and it's hard to come up with some good numbers. So this is from a report from 1999. I'm sorry, I think I got two sources there. But a municipal water and wastewater survey done by Environment Canada for 2004-2009. So while it may look a little bit dated, we've got to really realize that we haven't had that much change. So according to the 2009 Municipal Water and Wastewater Survey, 87% of Canada's population is served by sewer connected to some sort of treatment. And one of the reasons I say that it's not too critical when we talk about how old this data may be, you're looking at something that's 10 years. Well, this study has gone back into the late 80s and has not seen much change in the number of households that are connected to municipal systems. So we have 87% to municipal systems, and we have 13% of wastewater management is private septic systems. And when we say private septic systems, these might be individual systems at each property, or it might be a communal system where you have a handful of houses that discharge to a common drainage on-site leach field. So you can see that, for the most part, a lot of the households within Canada are served by a municipal sewer system. I was talking earlier in the week with Stefan, and maybe you can help me with this one, Stefan. You were telling me what part of the Canadian population is right on the U.S. border. I mean, was it something in the 90s you said?
A lot. Yes, as Canadians, we know that we are definitely within that 100 miles or whatever it is of the U.S. border, for sure.
Yeah, so when we look at that 87% of households, as you would imagine, a lot of that is going to be concentrated in the more urban areas along, in that big population density areas, and then areas expanding outside of it to the more rural and communal. And then when you look at the private septic systems, those are going to be your really rural areas. Excuse me. So we'll look first at kind of the on-site systems. And this is some information I got from a study that was done by the Federation of Ontario Cottagers Association. So again, it's one data point, but I think generally we would find that this translates pretty well to what we might see throughout Canada. And even speaking to that point, let me jump back real quick. When we look at these Canadian households where we have 87% connected to municipal sewer systems, 13% connected to septic, these numbers are very similar to what we see in the US as well. I think it's more like maybe 85% versus 15%, but very similar numbers. So when we look at sort of this data point of the classes of on-site sewer systems, even though this was done by a study in Ontario, I think we could have some comfort level in agreeing that it would apply to different provinces as well. And here you can see that most of the on-site systems would be what are class 4, which is the septic tank and the leaching bed. I look at this and I think anyone in the wastewater industry knows that there's actually class 6. You go from the septic tank leaching bed down to the cesspool and outhouse, which goes right into the ground. But there are some places where you got straight pipe into a water body. And that becomes an area of concern when we start looking at some of the pollution that we have because of failed septic systems, which I'll touch on in a little bit later. But here we can see that for the most part, when we talk about on-site sewer systems, we're looking at a septic tank and a leaching bed. Then we turn our attention over to the 87% of Canadian households that are connected to a centralized sewer system. When we talk about centralized sewer systems, we're looking at two primary types: separate sewer systems and combined sewer systems. So with a separate sewer system, you have a sanitary sewer that transports domestic wastewater, that's from residences, commercial, as well as industrial, transfers it to the wastewater treatment plant for treatment. And your sanitary sewer, which is a separate line, that discharges right to an outfall pipe, and it just collects stormwater from rain events. So when you have the wet weather, you have the separate storm sewer going to the, as shown in the picture, the outfall pipe to the river or to a lake. The sewer goes to the wastewater treatment plant. The other type of sewer system we have is combined systems. And this is where the sanitary and storm sewer are collected in the same system. So you're going to see these primarily some of the areas around, definitely near the water bodies, some of your older urban areas throughout Canada. I do apologize, I haven't done my research, but I know in the US you cannot get a permitted CSO anymore. I got to believe it's the same application in Canada as well, but you do have combined sewers that still have a permit and are allowed to operate with very minimum treatment during wet events. So with the combined sewer system, during dry weather, all the water goes to the wastewater treatment plant for treatment. But when you have that wet weather, anything over capacity, you have your pipe that has both your domestic wastewater as well as your storm water. And anything over capacity for the wastewater treatment plant is diverted to the combined sewer treatment or outfall, depending on what sort of treatment you might need for that. So again, these aren't really common systems anymore, but they still do have some that exist. And this is one of the reasons we start looking at maybe how do we address this as a problem. And it's something that we got to be aware of. And like I said, you're going to see these primarily in more urban, older cities, perhaps maybe around the rivers or the Great Lakes. So when we look at what we have within the centralized sewer system, I mentioned the domestic wastewater, and that includes the residential, commercial, and institutional. Now, part of what we have, even if we have a separate sewer system, you're still going to see that there is another component of wastewater within that system, and that's stormwater that enters the system that's not supposed to, or infiltration. And I'll go into a little bit more of how the stormwater that infiltrates or inflows into the system becomes a problem as we proceed. But you can see for the most part, and this is from a report from Environment Canada, the 2010 Municipal Water Use Report. So you can see most of the wastewater on centralized systems is residential, with about 18% of it being industrial and commercial. So as we look at the centralized sewer systems, everything on the on-site is going to be treated on-site. But when we look at centralized sewer systems, we all more or less are familiar with the conventional gravity sewer. That's been around for a long time. But there are actually quite a few alternatives. Well, if one considers quite a few. But we do have other alternatives. We have conventional gravity sewer, pressure sewers that incorporate grinder pumps, septic tank effluent gravity or septic tank effluent pump systems. These are systems where you have a septic tank on the residential property. The solids are retained in the septic system, much like they would be with an on-site system. But instead of the effluent going to a on-site leach field, the effluent goes to a treatment plant for treatment. And then you have vacuum sewers, where the prime driver is a vacuum that pulls the wastewater towards the ultimate collection point. Now, why do we need to concern ourselves with our wastewater collection system alternatives? There are many reasons that we need to consider wastewater collection. It might be an area where you're looking to expand a sewer service area. You have an existing service area, you're getting some development, so you need to expand that area. So that's either new development or old development adjacent to an existing area that you want to expand in and pick up that customer service base. One of the big reasons that we start to look at wastewater collection considerations comes down, though, to the wastewater management deficiencies. And we have these deficiencies both for the centralized sewer system as well as the on-site sewer systems. So when we look at the deficiencies, let's focus first on the septic systems. Septic systems have a limited service life, and they also have a costly life cycle. As you would know from my presenting on a wastewater collection system, I'm in the wastewater industry. I'm very familiar with it. I also have a septic system. And my septic guy, every time he comes by my house every 3 to 5 years to pump up my tank, tells me that I'm probably the only person who does it regularly. And I think we all kind of know that when you put a septic system in the ground, you tend to forget about it. Or the homeowner may not even know they have it. And that's a problem because you have that initial installation cost that is based and designed around the existing soil conditions, but those change over time. So you really got to maintain and take care of your on-site sewer system, or it's going to become a problem. So when it becomes a problem, you have some home depreciation. You also have the cost associated with inspecting, testing, and maintenance. And if the field goes wrong, you got the cost with putting in a new septic system. Now, I looked at a report, and again, this is kind of one data point. It's from the Ontario report I mentioned earlier. But they did an evaluation. They found that 41% of septic systems have major deficiencies that impede the functionality of the system. And we look at this graph on the left that was provided by the FOCA's report, and you can see that 32% on-site systems had no deficiencies, but 27 had minor deficiencies where the field might still be functional, but repairs or upgrades were required to ensure its future performance. But 41% had significant problems in the way the septic system and particularly the on-site leach field functioned. This can be a big problem because when you get failing septic systems, that can cause dangerous algae blooms in coastal areas, small lakes, or even to a certain extent, maybe the Great Lakes. It's a lot of water, but it still could become some problems. Also, you're having the wastewater that leaches right into the ground. When properly designed with good ground conditions, it may not be a problem, but as these systems fail, then you got private drinking water wells that can be contaminated. So that's something you definitely need to consider when you look at the deficiencies associated with on-site systems. Now we'll turn our attention over to the centralized sewer systems. And these would be primarily, when we talk about deficiencies, we're going to talk about failed gravity sewers, because most of the sewer systems that we do have in Canada and in the US are gravity sewer systems. Now there's one truism with gravity sewer systems. Over time, the gravity sewer systems are going to fail. It's not uncommon to have that over time be less than a year. It was a bad construction that the joints weren't made proper, where you have wastewater, groundwater, or stormwater get into the system from day one. In most cases, it's just that the pipe is going to get older and become a problem. So as I say, over time, the integrity of the sewer systems develop deficiencies. These deficiencies lead to problems. The extraneous flows overload and stress both the wastewater collection and the wastewater treatment system. And these extraneous flows are broken down into two categories: infiltration, which is groundwater that seeps into the sanitary sewer through cracks, joints, or other deficiencies on the sewer pipe or the sewer manhole. And we can actually break infiltration down to two components: dry weather infiltration and rain-derived infiltration. So during dry weather conditions, if your groundwater table is below the pipe, you don't have a problem. When it rains, you have that groundwater table rising, and the rainwater as the rainwater seeps through the ground, it will enter the sewer through those deficiencies. Or the other part, dry weather infiltration, maybe the groundwater table is above the sewer pipe. So even if it's not raining, you're still going to have groundwater that is going to infiltrate into the sewer system through the cracks and the joint deficiencies. The other component of the extraneous flows is inflow. This is rainwater that enters the sanitary sewer system directly. And this could be through a manhole. It may not be a lot of flow, but you see a lot of manholes that have holes in them, designed that way. Not so much now as it used to be, but that used to be kind of a standard design where you'd have through hose and manhole covers. You also have catch basins that might be improperly tied into the sewer system. And then of course you have inflow that comes during rain events from homeowners, where it's either a rain downspout from the roof is tied directly into the gravity lateral, or the homeowner has a sump pump because they have a flooded basement problem when it rains, and that sump pump discharges into the gravity sewer system. So these are where we see our failed gravity sewer systems. And again, the one truism is a gravity sewer system over time is going to develop deficiencies. And these deficiencies can lead to failure. It's just a matter of how big a deficiency and how big a failure. So that failure, as you see here, could be a basement flooding, a road collapsing, or just pollution within the water, with the waterway. Let's see, there we go. Now, so these extraneous flows, this inflow and infiltration, it doesn't cause catastrophic failure, but catastrophic failure is not the only thing we have to be worried about. Even if it doesn't cause the road to collapse or the water bodies to be closed because of pollution, it can still be detrimental to the community. The failure can be caused by the stormwater and groundwater, causing the capacity of the sewer systems to be exceeded. And the sewer system becomes exceeded to a much higher level, then you're going to run the risk of having sanitary sewer overflows. And these are going to be overflows either through lift stations, out of manholes, maybe at the treatment plant. And in my opinion, the worst kind of sanitary sewer overflow is when it backs up into a basement. Now, if you don't have wastewater backing into a basement or coming out of a manhole, you still have a problem with this I&I because it does reduce the overall collection and treatment capacity at both the collection system as well as the treatment plant. You got extra water that is in the system that has a treatment cost and a transportation cost as well. So even though it's clean groundwater, clean rainwater, once it enters the sewer system as infiltration or inflow, it becomes dirty water and has to be treated to the permit limits. So let's see, I'm not sure who's the organization, I forget. So let's see, the infrastructure. Okay, it's a whole bunch of organizations that do this, but they put together a Canadian Infrastructure Report Card. And this is some data from their 2019 report card. And it shows, has it broken down into linear wastewater assets, where they're looking at just the pipelines as opposed to the pipelines and the collection system, or I'm sorry, the pipelines and the treatment plant. Down in the US, we have a similar report card that's done by the American Society of Civil Engineers. And what I like about the Canadian report card is it has that delineation between the linear assets and the treatment assets, whereas in the US, it just groups wastewater all together. But here we can see from the 2019 report that 57% of the linear wastewater assets are considered to be in good or very good condition. That means the remainder, 40, I'm gonna do quick math here. 43% is fair or less than fair. So you got 70% that is in fair condition, 11% in poor or very poor condition. And one of the things they really pointed out in this report was that last number, 15%, where the condition is not known. And where that becomes an area of concern is there's a large portion of the linear wastewater assets that are more than 50 years old. So one of the things they looked at in developing this report card, they found that 30% of sewer pipes with a diameter less than 450 milliliters were installed before 1969. And 75% of sewer pipes with a diameter less than 450 millimeters is more than 20 years old. So here, we got that 15% where the condition is not known. There's a very good chance, according to the report, that the condition is bad because this is some of the older pipe that would be in the system. If you don't know what the condition of the pipe is, chances are it's not the newer pipe that you're looking at or having problems with. So we can see that there are wastewater deficiencies within the collection system throughout Canada. Now, the standard approach when you look at these failed wastewater assets is to do a sewer renewal program. You get this gravity sewer that is failing, so you want to look at these progressive actions to return the functionality back to normal. And here we're looking at a couple options of repair, rehabilitate, and replacement. Now, I have I think a whole 45-minute presentation just on this alone, so I'm just going to give you the quick overview. But sewer repair is when you have the gravity sewer that you have a short repair or a short problem that you can get in there and put in some grout in, maybe fix a joint or a small piece of pipe to get everything back to its operational capabilities. Rehabilitation, you get the failed gravity sewer and you're going to put in a liner, a CMPP liner or fold and form liner, So you're using the existing failed gravity sewer and putting in a new interior to that. And then the other alternative is sewer replacement, where you replace your failed gravity sewer with another sewer. And the problem with sewer replacement, to replace the failed gravity sewer, is it has a high social cost. You're running into a lot of issues here. So we really want to minimize that. And one of the ways we do that is look for a better sewer replacement solution, which is low pressure sewer system. So now we want to look at 2 of the 4 systems where we have conventional gravity sewers and pressure sewers with grinder pumps. Conventional gravity sewers are designed to take advantage of gravity as the prime driver. Gravity sewers have been around forever. First sewer system was developed 4000 BC by the Mesopotamians. So they've been around for a while. Low pressure sewer system has been around for a lot less. The design installation of gravity sewer systems is dependent on maintaining a constant downward slope so that you maintain acceptable flow velocities. If the topography is flat, the sewer pipeline is going to be installed at increasing depths. This is going to cause the trench excavation to get deeper, and it becomes unsafe and uneconomical to continue. In this case, the lift station would be required. So the system consists of service laterals, large diameter mainline sewers, manholes, lift stations, and other appurtenances. I'm going to go into a lot more detail on these individual components in part 2 of the webinar series. So this is just the teaser. Advantages of conventional gravity sewer. You got 2 real big ones. It's a simple, reliable operation on the sewer itself. You install a pipe, the wastewater enters the pipe, the wastewater flows downhill. Procedures for the proper design and operation for gravity sewer systems are well established. Now, when we look at the disadvantages, you have some high capital costs because you have a deeper excavation. You may not be able to do the entire system on gravity, so you would have some lift station. These kind of impede the ability and the flexibility for future expansion. If you have a system that you're designing, the end of your system is going to be at the higher point in the system. So in order to get more wastewater introduced into the system, you're going to have a lift station required in most cases to do that. The mains need to be laid at a precise grade. You have to make sure that flow is going downhill to maintain the proper velocity. As I mentioned, you got lift stations that may be necessary in most cases. And as I already went through, there's the high probability, if not certainty, that infiltration and inflow is going to be part of the gravity sewer system. So now we want to look at a pressure sewer system. As I said, gravity sewers established 4000 BC. Pressure sewers established 1969. So this is not as well known. But what a pressure sewer system is a wastewater collection that uses individual pumps located at each property, be it a residential property or a commercial property. And it conveys the flow to the treatment system, to a lift station, or can even convey the flow to part of an existing gravity sewer or force main. It's one of the advantages of it is it has a lot of flexibility on where the wastewater is ultimately conveyed to. The system consists of individual grinder pumps and small diameter pressure mains. For the most part, the pressure mains that are used are going to be between 40 millimeter and 100 millimeter pipe. And it's going to be flexible and buried just below the frost line. And one of the advantages is it can follow the contours of the land. I thought I had another slide in there. So the small diameter pipe is flexible and it can follow the contours. So when we look at the advantages of pressure sewer systems with grinder pumps, as I already touched on, small diameter pipes, shallow installation, this is going to yield lower capital cost. You got smaller crews installing more pipe installed per day. So your installation rate is much faster. Your pipe costs are down, your crews are smaller, and your overall cost will be lower. Also, in many cases, you're not going to have a lift station, so you don't have that added cost that you do with the gravity sewer system of having to install a lift station. Because the pipe sewer system does not require a precise grade that is required with a gravity sewer system, you don't have to worry about being that precise, and that allows the opportunity to use trenchless methods. One of the things that we also talk about in this is with a gravity sewer system, you're going to have a manhole installed about every 900 to 150 meters. With the pressure sewer system, you don't have any manholes, so you can use trenchless methods and drill a longer length than you could if you were trying to use trenchless methods on a gravity sewer system. Lower social costs and lower environmental disturbance envelope. And I kind of touched on this. These are the non-economic costs, and we're really going to go into more detail on these costs in part 3 of the webinar. So I want to make sure I leave you all with just a little bit of teasers to keep you coming back for part 2 and part 3. Another key component is it does not require any central infrastructure. If a grinder pump at one property fails, it does not impact the rest of the property. Maintenance can go in there, replace that one core, and have everything up and running, and you have no failures throughout the system. And one other key component, no stormwater infiltration. That significantly reduces the burden on downstream infrastructure. If you have a wastewater collection plant that takes 100% of the flow from a low pressure sewer system, you do not have to design a lift station for I&I. You do not have to design your treatment plant to handle that excess flow. And we know when we look at peak flows, that flow contribution requires the industry to design downstream infrastructure much larger than is really needed to handle the domestic wastewater flow. Disadvantages with pressure sewer systems. And these disadvantages, depends on how you really look at them, how hard or soft they can be. But each building in the system requires a grinder pump unit. This really kind of goes both ways, a disadvantage and advantage, because when you're looking at the types of pumps, you have different types of pumps, semi-positive displacement pumps and grinder pumps. I'm going to speak to that a little bit later or shortly. But if you have a semi-positive displacement pump like E1, requiring a pump at each property is not that big a unit because these pumps are interchangeable. Some other things that might be considered disadvantages is you want to keep some spare parts on hand. I mean, it is a piece of mechanical equipment. E1's pump has a long mean time between service, exceeding 10 years in general, but it is a piece of mechanical equipment that might fail. So you want to make sure that you have another pump that you can pop in there if there's a problem. Each pump is dependent on acceptable electrical service. It may not be a problem in the majority of areas, but if you're looking at maybe a lake community cottage where the electrical service might have to be upgraded, but in most cases, that's not really a big problem. And the big one, when I talk about disadvantages, is that it's a newer application. Not everyone is as familiar with low pressure sewer systems in terms of design and operations as they are with a gravity sewer system. So here I'm going to go through the history really quick. I already mentioned gravity sewer system has been run a lot longer, but the concept really was developed in the late 60s, and it was driven by a need to get rid of the combined sewer systems. So in 1967, under the direction of the U.S. Federal Water Pollution Control Administration, which is now the U.S. EPA and the American Society of Civil Engineers, they did this study to look at separating the wastewater and the stormwater in combined sewers. And Dr. Fair came up with the concept of a pipe within a pipe, where a small diameter pipe would be hung from the crown of the combined sewer system, and then the material would be ground up. So General Electric was contracted by the ASCE in the study to develop this new household appliance. And what was nice about this concept is this was a group of appliance engineers, not a group of pump guys who were trying to figure out how do we make our pump work for this application. The design team at General Electric went in there with the attitude of what appliance do we need to solve this problem? And they concluded that for a low pressure sewer system, a progressive cavity semi-positive displacement pump was best suited. Not sure exactly what happened, but in 1969, I was only 4, so I wasn't really paying attention too much to the industry. But they decided, General Electric decided they did not want to be in the wastewater game, and the General Electric design team went on to become the founders of Environmental One, setting up shop in what is still our office today in Niskayuna, New York. Once they established a proof of concept, other manufacturers followed. So it is a proven technology, but it's only been around 50 years. Gained popularity in the early years due to the ability to provide central sewer service in areas where gravity sewer system could not be installed, or the cost to do so would be very expensive. Over the years, based on the experience, we have shown that there's a demonstrated advantage, and that has expanded the use of pressure sewer systems. So now, instead of being seen as the alternative when there is no alternative, pressure sewer systems are starting to be seen as the appropriate wastewater collection system. Even if conceptually gravity sewer system makes sense, it still might be valuable to consider a low pressure sewer system. And this competitive alternative, this competitive approach is driven by the lower environmental impact and social cost associated with low pressure sewer systems compared to gravity sewers. Already mentioned most of this, but the increased construction schedule, you have a better construction phasing with low pressure sewer system than you do with gravity sewer system, lower capital costs, and a lot more flexibility. So when we look at a low pressure sewer system, we look at what I'll call the heart of pressure sewer system. It's actually the hearts, because you'll have this at every location. Every manufacturer is going to be different. As I said, the concept was developed by the E1 Corporation, or rather General Electric, that went on to become the E1 Corporation. Other manufacturers followed. So everything's going to look a little different depending on the manufacturer, but you're going to have the same components. You got your pump basin, your pumps, which can be either progressive cavity, or in the case of other manufacturers, centrifugal. You get your liquid level sensors, tell the pumps when to turn off and on based on the water level within the basin, the pump controls that actually do that, and then a pump removal guidance. So with the E1, everything is on one core, and it sits in a funnel. So the removing the pump is very easy. Just pull it out of the funnel with the rope that's attached to it. If you're looking at a centrifugal manufacturer, you're probably going to see something more akin to a rail system that you would see on a larger lift station. And what's really important to remember as we kind of go through this is the concept with the semi-pod displacement pump that was developed by Environment One Corporation was geared towards looking at it as an appliance, where you want it to be as low impact, no attention paid by the homeowner. You know, that you don't want to pay more attention to your grinder pump any more so than you would your washing machine or your refrigerator. So the basic system works where you have the grinder pump that is located in the yard or basement of each home. Wastewater flows through a standard lateral from the house into the pump basin. The basin contains the grinder pump with the integral level controls. With the E1 system, it is all part of the E1 core. I'm not going to go into any of the features and benefits or the details of the pump itself. If you do want more information on that, please contact the guys at John Brooks, and they can walk you through, you know, how our core is set up and how everything is in that one unit. With the centrifugal pump, you're going to have the floats that you would normally see again with a larger lift station. Those floats can be a problem and a nuisance depending on how you're operating it. So the pump is activated when the sewage in the tank reaches the predetermined level. The wastewater is ground up and discharged to the lateral until it reaches the off level, and then the pump turns off. Here, the runtime is short. Power consumption is very low. With the E1 system, it is a 1 horsepower, low velocity, high torque pump. Centrifugal pumps tend to be 2 horsepower, but in both cases, the runtime is short, where the daily operation is generally no more than 20 to 30 minutes per day. So you don't have a large power consumption with a 1 horsepower pump running only 20 minutes per day. So as I said, the wastewater is ground up and then discharges through a small diameter pipe. It'd generally be around, I want to say about 20 millimeter, maybe 20 to 40 millimeter going to the sewer main. And then once you get to the low pressure sewer main, that pipe is going to be typically 40 to 100 millimeters. If you have a very large system, you might see, it's called 150 millimeters. But, you know, we did an evaluation looking at a whole lot of low pressure sewer systems design. And these were studies, designs done by other consultant engineers, also including other manufacturers. And as a system, we found that 95, or I think it was 94% of all the pipe in a low pressure sewer system was 100 millimeters or less. So you have small diameter pipe throughout the system. Quickly, I don't want to go too long, but as we look at this, I mentioned the types of pipes. When you're looking at a low pressure sewer system, the type of the pump can matter significantly, because the way the system operates, and if you come back for part 2, we'll go into some of the design, but basically you have, let's call it 200 pumps in the system that are going to be turning on and off at various times. So you have parallel operation with multiple pumps, but each one of those pumps is operating for less than 45 seconds. So you have a lot of dynamic stuff happening within the wastewater collection system. And how that is handled really matters on what kind of pump you have in there. So you have 2 types of grinder pumps used in low pressure sewer systems: centrifugal pumps and progressive cavity pumps. With centrifugal pumps, and this is when we talk about wastewater, most of us that are familiar with wastewater pumps are familiar with centrifugal pumps, and that's where you have that rotating impeller that imparts that rotational energy on the pumped fluid. It is greatly affected by the system pressure. As the system pressure changes, the pump operation, the pump characteristics will change. The pump discharge characteristics will change. Now, this isn't a problem if you're working on a major lift station where the engineer can have a good sense of what the flows are going to be, what the head losses are going to be, and what the best efficiency point is going to be. But when you're talking 200 centrifugal pumps that are going to be operating for less than 25 seconds, or I'm sorry, less than 45 seconds each, as I said, you have a very dynamic system. So your total dynamic head within the system is going to change drastically. And that may require either different size centrifugal pumps or impeller customization. Now, progressive cavity pump, or what we'd call a semi-positive displacement pump, uses a stainless steel helical rotor and stationary elastomer stator. If you're familiar with progressive cavity pumps, you're probably familiar with them, assuming it's not in the low pressure sewer space, you're probably familiar with them in the solids handling part of the wastewater treatment, or chemicals, or something where you want to move something other than water. And how it operates is with the rotation of the rotor. The rotation of the rotor creates these series of cavities that moves the fluid to the discharge point. So it becomes a plug flow type operation. The wastewater is ground up and then discharged and moving from one chamber to the next chamber to the next chamber. What really makes this design for wastewater collection, and specifically low pressure sewer system, is you have that constant discharge where no matter what the total operating head in the system is, the pump is going to discharge a near constant volume. So we're always going to discharge somewhere between 6 to 12 gallons per minute every time the pump discharges, regardless of where it is exactly on the system head. And like I said, this is critical because when you're looking at multiple pumps operating on and off throughout the system, your dynamic head is going to change a lot. So here, if you look at the curve B is the total or the pump operating curve for a semi-positive displacement pump, where you could see no matter what the total dynamic head is and how many pumps are on or off, the discharge is going to be very similar. Compare that with curve A, and you see those lines on the horizontal, the 1, 2, 3, 4, on the right-hand side of this graphic. We kind of use that to represent the number of pumps on in the system. So as you have very few pumps on in the system, your total dynamic head in the system is going to be low. Your centrifugal pump is going to be operating on the far right-hand side of its curve in the cavitation zone until more pumps come on. As more pumps come on, then one of those pumps will start to operate in the best efficiency point, but it's not going to be there for too long because when more pumps come on, more pumps are going to be turning off. And if you have a lot of pumps come on, let's say we're looking at the 8 or 9 pumps come off, then the operating point in the centrifugal curve will move to the left-hand side. And within seconds, it will move to the right-hand side. So you have this centrifugal pump that is never operating at its best efficiency point. And not only is it not operating at the best efficiency point, it is going from the left-hand side of the curve to the right-hand side of the curve, going from cavitation to recirculation during a typical day during the cycles. Whereas with the curve B, it's always going to discharge that constant volume. You know, one of the questions we get asked a lot is, what is the best efficiency point on the E1 pump curve? Because when you're looking at a pump curve, one of the things you want to concern yourself is the best efficiency point. Where does this pump work the best? Well, with the E1 pump curve, we don't have a BEP because the entire curve is essentially our best efficiency point. We operate well throughout the entire curve. So when you look at it, that's why I say it's important that not only do you want to look at low pressure sewer system versus gravity when doing an evaluation, but once you get into the low pressure sewer system, it's important to look at the actual type of pump that you use. And again, this is just kind of the overview on low pressure sewer systems and gravity sewers. If you want to get into more details, I got another 45-minute presentation just on the difference between the A and the B curve. So, certainly if you need more information, please follow up with E1 or with John Brooks and we can get you that information. So this is just a quick summary when we're looking at gravity versus low pressure sewer system, the issues and comparing the two. And I'm not really going to go over this because I touched on most of it throughout the presentation. But infiltration and inflow is something you need to consider. It's avoided with pressure sewers. It's included in the design with gravity sewer systems. You have lower capital cost, shallower excavation. I know to get down to the frost line in Canada is a lot different than getting down to the frost line in the southern US. So not only do you have to maintain that constant slope, but you might be looking at a depth of sewer there of 20 to 30 feet in normal conditions. Lift stations are a cost that you want to consider, not only a capital cost, but lift stations for gravity sewers are also an operation and maintenance cost. So that's important to keep that in mind. And again, when you look at this, and as we get into part 2 and part 3 of this webinar series, we'll really start to look at how these issues really compare between a conventional gravity sewer and a pressure sewer system. So what's next? That's my teaser. Now I do got to follow up because I did this presentation. I thought the next one, and Paul, you may want to correct me. So part 2 is on May 14th, you said, at 2 p.m.?
That's what I had in my notes. I'll confirm it. Martin?
I thought that was...
That is incorrect. It's May 21st as Keith has it on his slide.
Okay.
Yeah, as soon as you said that, Paul, I realized I don't have time to change it, so I have to get the rest of this. So what's next? May 21st at 1 p.m. And I put the p.m. there just so none of you get up at 1 in the morning to hear me talk. And what that is going to do is look at a deeper dive, the system components, the basic design principles between gravity sewer system and pressure sewer system, and then look at some of the operation and maintenance cost. So with that, hopefully we got a few questions out there that we can talk to. And I guess, Stefan, I'll turn it over to you for any questions that we might have or we're seeing.
Paul, would you mind reviewing the questions? I think Stefan was.
Yeah, we have one question that's come in. Could you speak to any advantages, disadvantages to pressurized systems in colder climates?
I would love to defer to the guys at John Brooks for that because I know they do have definitely addressed it more than we see down in the States. So what do you guys see with the colder climates?
Everybody, Martin here. I would like to mention that usually what we see in Canada are effectively deeper installations. Laterals and pressure mains are often installed below the frost line. So typically between 4 to 7 feet is where we'll find our pressure mains. And that's usually sufficient for the vast majority of installations. You can also install HDPE pipes, insulated HDPE pipes, which will help also to prevent having such a deep installation. So for more, if you're thinking for people who have some rocky installations, we might have to excavate at a shallower level. So that's when we'll put insulated HDPE pipe. And we also have heat cable kits available for those extreme situations, just as a safety. Hope that helps.
Great, thanks, Martin. Another question, does the homeowner own the pumps and are they responsible for operation, maintenance, replacement, etc.? And otherwise, what are the access considerations?
Yeah, I always like to rephrase that question because that's a question we do hear a lot. And I like to rephrase it with who owns the pump, the homeowner, the municipalities, or somebody else? And the answer is yes. It really changes. many of our systems, and I don't know that we have a good breakdown, but I would say probably greater than half the systems are owned by a municipality, maintained by a municipality. E1 is based in New York, and the code in New York requires that for low pressure sewer systems, or actually for any sewer systems, the municipality has to be responsible for the maintenance. Now that responsibility could include subbing out or having a contract from a third party service provider to take care of that. But it really doesn't, it does change location to location where, some places the municipality is responsible for installing, owning, and maintaining. Other systems, the municipality will put in the mainline sewer, and the homeowner is responsible for purchasing and buying the grinder pump and then maintaining the pump. Then you have the other ones where the municipality also pays for the grinder pump, but the homeowner maintains it. So it really does change. And here I'll turn back over to the Stefan or any other John Brooks guys to see, do you see that different in Canada? Do you have that diversity in the ownership model?
It's identical in Canada, Keith. In Canada,
Yeah.
You'll have a mixture of municipality-run or homeowner-run pump stations. For sure, the low-pressure sewer system, the actual pressure mains are the responsibility of the town, but the actual responsibility for the stations will be 50-50, we see in Canada. And that will also, to answer the previous question as well, with regards to colder climates, we have many homeowners who decide to install the pump stations indoors. So E1, similar to their initial pump station, have today an IH091, which is an indoor unit, which people will install in their basement. And so for those extreme cold climates, we have that one as well. And so that is why sometimes you'll have some municipalities that will leave the operation of the pump to the homeowners.
Thank you. And to touch on the second part of the question, the access considerations, regardless of who owns and is responsible for the maintenance of the pump, you want the pump to be accessible. There's the cover on there that you don't want to put it underneath a deck. You can landscape around it, but you want to make sure that the water, the rainwater flows away from the cover, so that if someone has to get in there to access the pump or even just do a quick inspection, although no preventive maintenance is required, you want to make sure that the pump is accessible. Now, if it's municipal owned and maintained, they might have their own requirements in terms of the easement, that they don't have to walk across the fence or something like that. But even if it's privately owned, you do want to maintain that the cover is accessible, because once you move that cover, that's all you need to get to the pump.
Great, thanks. So another question, how long is the owner offline during grinder pump replacement or failure?
Really not that long. I mean, if you're talking a mechanical problem or something where the pump needs to be serviced, what's really nice and integral, like I said, it all really goes back to our founders in the late 60s when they were a group of General Electric engineers. So they designed this system as an appliance. So everything that you need is in the pump core, which, the pump core is the pump I have on the, right-hand side of the screen. If you need to access it, you can just pull that out. So I would say it's less than, it's minutes that the pump would be out of service, assuming it's nothing really a big issue. But yeah, there's
okay, I think I don't see any other questions coming in right now. Closing in on the 1 hour mark here. So unless there's any further questions, we look forward to everybody participating in part 2 on May 21st at 1 p.m. And the invites for that will be going out. And as I said earlier, we'll be sending out a link to the recording of this video or of this webinar as well. So Keith, unless you got any other comments, I think that kind of wraps things up.
Yeah, and again, thank you for the opportunity to join you all today and go through this presentation.
Yeah, great. Thank you, everybody, and we look forward to seeing you on the 21st. Have a great day.